First of all, thank you all so much for coming and joining us today. It just makes this day so important and worthwhile to see everybody come. And hopefully we are providing some useful information to everyone. So thank you all for coming. So I am Brad Christian, and I am a researcher here at the Weizmann Center. And I want to talk to you about an ongoing project that we've been conducting for about 10 years now, and that's looking at the connection of Alzheimer's disease with Down syndrome. I've given this a discussion on this in the past, and today I'm hoping I can kind of direct you towards where we're going to go. Hopefully we're getting closer and closer to prevention or type of treatment trials. Okay, so I want to just lay out the association first. Some of the imaging that we're doing to measure biomarkers for this disease, and then get more into the study results that we found so far, and finally looking towards the future and where we're hoping to go with this. Okay, so Alzheimer's disease, we'll get to the numbers right away. Just in the general population, it's very rare before age 50. However, there are cases of it there, and that's typically what we call early onset Alzheimer's disease, and that's people with a genetic predisposition for it. Otherwise, if we consider more of our late onset Alzheimer's disease, it becomes more prevalent as you get older, and it isn't until you're in your 80s that we're seeing about a third of the population having Alzheimer's disease. But let's compare this now with our Down syndrome population. Here we are seeing it at an earlier age. I have 9% there in their 40s. And in their 50s, now we're at about a third of the population. So if we contrast that with the general population, we have about the same prevalence, but 3 decades earlier. Okay. And then as we get into our 60s, the prevalence becomes much higher. So we're seeing it higher incidence at earlier stages in life. So briefly, I think everybody here knows Alzheimer's disease when they see it, but a more formal definition, I guess, first of all, for dementia, we talk about a deterioration in cognitive function that prevents a person from doing their normal daily activities, living independently. And of course, Alzheimer's disease is the most common form of dementia. About 70% of dementia we would call Alzheimer's disease, and that has difficulty in what we would associate with Alzheimer's, typically language, memory, and various cognitive skills. Alzheimer's disease, of course, is a public policy issue. We have over 5 million people, and as our baby booming population gets older, we're going to see more of it. Of course, age is a risk factor, and there's nothing we can do about that as we grow old. The incidence is going to be higher, and of course, our population is growing older, so there are going to be many new cases of Alzheimer's disease coming in the future, and we know that it has a huge burden on society with the healthcare system, and people typically, when you develop Alzheimer's disease, you can live with it for an extended period of time, and the health burden is quite great. So then the government recognizes this, I think, being promoted by voters too that want to see more action on this. You can see the amount of resources that have been put into it. In the 2013, we have about $500 million, and then it escalates. In this year, it's up to $2.3 billion that the National Institutes of Health are committing to Alzheimer's disease and research investigations in that area. So we'll go briefly through the pathology of it. That is, what's going on in the brain, what are we seeing in changes in the cells. So when Dr. Alzheimer in the early 1900s actually did an autopsy on a person that had dementia, looked at the brain, and there were some signature features. And these were what were classified as these plaques and tangles. So amyloid plaques would coat the surface of the cell, and these tangles were more bundles on the inside, and they kind of spread in patterns that were consistent across the people afflicted with this disease. So I'll just briefly explain it and not get too steeped in molecular biology here, but I don't know if I'm going to be able to pull this off with a pointer. Okay, so what happens? This would be a cartoon of a brain cell, and all brain cells have proteins tethered to their surface, and one of them is this APP, amyloid precursor protein. So that belongs there. It's in the cells, and it has a function. And it can be cleaved off by certain enzymes. And normally when it gets clipped off, it becomes the soluble form, and that gets washed out of the brain and all as well. However, there's another pathway with a different enzyme, and that's this beta secretase right here, the purple one. That can, when it cleaves it off, it does it in a slightly different spot, and it leaves behind these fragments, these peptides, that are now sticky, and they can adhere to each other and start to gather together, form clumps referred to as oligomers, and ultimately they can all aggregate together and form these plaques. And these plaques are what can coat the surface of the cells, and that is what Alzheimer saw in the brain when he looked at it. And then the other pathological feature are these tau tangles, are called neurofibrillary tangles. And that is, tau protein is another protein that belongs in the brain. It kind of forms the scaffolding of neurons, and it can become degraded over time and gather, and these two can aggregate. Now, these typically are on the inside of the cells, and they can cause damage too. So it seems these features that I'll be talking about are the plaques and tangles, and I'll come back to those. So what is it about Down syndrome that would put them at increased risk for developing Alzheimer's disease? Well, Down syndrome, of course, is trisomy 21, and if we look at chromosome 21, there are a number of proteins that are encoded on this chromosome. And the gene for one of them is on chromosome 21. And I just talked about the APP. That's where it's encoded. So it is believed that in Down syndrome we have an overproduction of many genes, but this one in particular we can attach to significance in Alzheimer's disease. So there's too much of it. And that has been confirmed throughout the years in examining the brain and seeing it later, and it can be prevalent very early. Okay. So if we consider the life expectancy of somebody with Down syndrome, we know in the mid of the 20th century, it was only 9 to 12 years old. There were not medical procedures available at the time, and really didn't, the Down syndrome population didn't have as much access to health care either. And as medical advances were made, we can now see that somebody with Down syndrome born today will expect to live into their 60s or beyond and live long and productive lives. So this all comes with improved health care and access to health care. However, with growing old come the other diseases that are related to aging that are going to emerge also. Of course, Alzheimer's disease is one of them. So, there may be others too that we notice in Down syndrome, but focusing on Alzheimer's disease, this just is more of an illustration of the effects of when a person can get it. I was kind of giving gross categories before, and now if you break it up with age, here and the prevalence, we're seeing most people are developing it at about age 55. It can come as early as the late 30s and later into the 70s. And just like in the general population, it affects the survival of a person. So if somebody has Alzheimer's disease, they will not survive as long as somebody without it. So that's just like in the general population. So now I want to switch gears and talk about our research a little bit more and studying these biomarkers. And just to give you, I'll be using that word, and a biomarker is a biological marker And it's a medical sign that describes a medical state, and this is outside the patient having to describe it, and it has to be something consistent that we can measure. So rather than a subject describing, well, my memory's not so good, or my memory's bad, it needs to be something you can really quantify, and we have what we characterize as these biomarkers to do that are not so subjective. And the biomarkers for Alzheimer's disease are these plaques and tangles that I had just talked about, and neurodegeneration that also can be measured. And when Alzheimer's first diagnosed, he did it at autopsy, and of course through much of the 20th century, there was no way to see these plaques and tangles in the brain until somebody had died and you could actually look at the brain tissue. Well, now with the advances of medical imaging, we can actually detect and measure these biomarkers of the plaques and tangles while a person is still living in a very non-invasive way, either using magnetic resonance imaging or positron emission tomography. So I think everybody has a good feel for MRI. You lay in a magnet and we can measure the different tissue types. Well, with PET, what we do is you can take a drug and label it with radioactivity, put it in a person, and then measure to see where it goes. Now, the key is we only use very, very tiny quantities of these drugs, tracers, so the brain or your body really doesn't know it's there. It doesn't have any kind of pharmacological effect. But all of it hinges on the ability of the drug to go to where you, the process that you're looking at. And that's where a lot of advances have come about in this field, is designing drugs that either go to amyloid and can be imaged or go to tau. And we've been fortunate to make great strides in that area. So our motivation for looking at these biomarkers in Down syndrome is to start to stage and measure the trajectory of some of these biomarkers. For example, amyloid is the first one that we looked at. And we're hoping that these can inform future studies, specifically prevention or treatment trials. That is, if we have a target that we know a drug should try to clear out of the brain, such as amyloid, when should we give it, and is there a way to measure its effectiveness? So we need to first get a feel for how that trajectory is. And lastly, of course, this is the trials that I've been talking about, and the Down syndrome population is well suited because there's a high incidence of a particular disease. So if you can find people that have a higher risk of getting it, you can then focus your trials much better and hopefully get away with fewer people in testing drugs, and that makes it much less expensive to test these studies that are tremendously expensive. So, as I said, we started this study about 10 years ago, and we conducted what was called a natural history study. And these are the first kind of investigations you do when you're looking at a new disease. That is, you need to just see how the pathology behaves naturally and try to characterize that. And we were looking at the amyloid, and shown in the picture is Professor Segan Hartley, who is also an investigator here at the Weizmann Center and a close collaborator on this project. So our goal was to bring in adults that did not have dementia with Down syndrome and just measure the presence of these amyloid plaques in the brain and then track that with cognitive function that was conducted with various tests. So again, we could then examine the presence of the amyloid and then relate it to how it's affecting how people can function cognitively. We had 79 subjects, and this was a collaboration with the University of Pittsburgh, roughly half of the subjects at each site. Although the participants were older than 30 years, and as I said, we conducted the neurocognitive measures and then did our imaging studies too. So for the first day, they would come in and we would do a variety of tests, games that we call them, that kind of probe different components of cognitive functioning. Do they test memory? Do they test your ability to plan or your attention? And then the next day they would come in and we would do our imaging exams. And here is an example of the PET drug that we use, or the PET tracer. I'll call it PIB. It stands for Pittsburgh Compound B, and it was developed by our collaborators at the University of Pittsburgh. So this is a tracer that labels these plaques. We can inject a little bit of the radioactivity in a person and then scan them in the PET scanner. And if we see the presence of this red color in the image, that would be somebody, we're calling them PIB positive or amyloid positive. They have an elevated amount to this. And I want to point out, this is just a color scale we're using to it. It's not going to change your brain tissue red or yellow or green. This is just how we map it out. That throws people off sometime. So it's a little bit of radioactivity. Nobody's brains glow. Nobody glows at all. These are very safe procedures that we conduct. So we found that of those 79, 59 were what we call PIB negative. That is, we didn't see any elevation of amyloid in any of their brains. You don't see any red. This stuff in the middle is the white matter in the brain. We're not really concerned about amyloid there. It's more in the outside or the cortical areas. And then we found about 20 of the total subjects, that is roughly 25% of them, did have the presence of elevated levels of amyloid in their brain. So now we can relate this to the different cognitive tests that they took, and we classify them as PIB positive, meaning amyloid was there, or PIB negative, and look at the different tests where we actually did see a difference between the groups. So even though all of these participants were considered non-demented, there still might be subtle differences that the cognitive tests will show us. But that exam in itself, that's called a cross-sectional study. People come in, you scan them once, and you compare everyone across a group. A much more effective way to study people is something called longitudinal. That is, they come in and you follow them over time. You get much more conclusive results when you look at it in this longitudinal fashion. So we had everyone come in and we scanned them again, and our original one. So 52 subjects came in at 3 years later, and I want to point out we still had all of these individuals stay with our protocol. It's just at the time that we reported this data, because we were moving on to a different study, we had to stop at 52, but everybody stayed with us. There wasn't that high of an attrition rate. So now I can group these, a slightly different picture here. So what I'm showing is the percent change in this amyloid between the scans that were 3 years apart. And again, I color-coded it, and the green that you see here is really 0% change. So a portion of the people came in once, 3 years later, and we really didn't see very much change in their amyloid. So we're calling that the negative group. And then there were some that were negative at that first scan they came in, but then 3 years later converted to positive. That is, there was a lot of amyloid. And we're calling that group the converters because they converted amyloid status. And then we had the last group of people that had positive amyloid at baseline and then positive at follow-up, and they're just our PIB positive group. And you can see the patterns there. Roughly, we see 4 to 5% increase in this amyloid measure per year over time. And now we relate that to the change in their cognitive testing, that is playing those games that look in different dimensions. And we see in this positive at baseline, positive later group, there were significant changes in all of these, or the tests that we report here in memory as well as other components of cognition. Okay. So that was our natural history study. Again, we started that in 2009. In 2015, we transitioned to a bigger study. That is, the National Institute of Health was very interested in what we were finding. So they encouraged us to continue it and make it larger. That is, bring in more people. So we brought in the University of Cambridge in the United Kingdom and some other sites in the States and made it a larger number, and we increased the biomarkers that we were looking at. So we weren't just going to look at amyloid in this next study we call NIAID, Neurodegeneration in Aging Down Syndrome. So the NIH is advertising this on their website. Here it is, and show the NIH. This is our helper who has just been instrumental in making this happen and bringing this relatively large study together. And I won't go into all the results because this is ongoing and we've just started, but you can see now our numbers are up to 166 people in this. And this slide is just showing the amyloid results. So just to briefly explain it, wherever you see a circle, that is a new enrollee in the project. That is, we only have one scan on them. But where you see the lines, those are participants we've been following over time. Okay. And the red is color-coded to show that somebody is amyloid positive. Blue means they're negative. So I think what grabs your eye right away is as you get older, the positivity becomes much more prevalent. Right around 40, we're starting to transition into most people being amyloid positive at that point. So we're going to continue to add to these data as time goes on. But another thing, or biomarker that was included in this new study is looking at the tau protein that I was talking about earlier. So just within the last several years, there have been developed these PET tracers that target the tau. It's a trickier target to try to measure in the brain compared to the amyloid because it's at lower concentration. So a lot of trial and error, but now a radio tracer is available. And here are just kind of a summary of some of the findings we find, and I'll take a moment to unpack this a little bit. So each row shows a representative participant. So this would be their amyloid scan, their MRI in the middle, and here would be their tau scan. So the top row would show a participant that was amyloid negative, no amyloid there, and really no tau either. As we go down, I'm showing a participant with more amyloid, and now you can see tau start to become evident in the brain. And that is an area of the brain, the hippocampus. It's involved in memory, storing memories, retrieving memories. So that is starting to accumulate this tau protein. As we go up in levels of amyloid, we're seeing this tau start to spread outside there and start to be incorporated in some of the cortical areas of the brain. And our bottom row shows a subject with, or a person with extensive amyloid and tau present too. So we can relate these to one another. And on this, I'm just showing here would be the level of amyloid we measure, and here is the level of tau. And this would show where we're amyloid positive. So really there is not elevated levels of this tau protein as long as there are smaller levels of or lower levels of amyloid. But once we start to exceed that threshold, now we can see elevated tau in the brain. So this too is, we're continuing to acquire more data on this, and it's helping us form just what we call conceptual models. That is, exactly what is the time course. So we have to start off proposing a theory, and this is not unique to Down syndrome. This is a trajectory that's shown in late onset Alzheimer's disease too. But in essence, we have kind of time and disease progression, and the amyloid starts off at very low levels, and you start to see a period of accumulation, and then there's saturation. Now, we're finding that tau accumulates after that, same type of trajectory. Now, again, this is just kind of proposing what it looks like. And then after that, we see what I have labeled synaptic dysfunction. It's just showing that your neurons are starting to become damaged in the brain and not working as well. And we have biomarkers that can start to detect that. And then we have death of the neurons. And once the neurons die, shortly after that, now we're seeing the decline in measured cognitive function. That is, your memory isn't working as well. Behavior is starting to be altered. So it's fairly late stage after these early biomarkers become prevalent. So we can use this to decide if we were to try a drug treatment trial or prevention type of trial, to set our thresholds and determine exactly where they should be started and what we should be looking at and what type of time course. So if you were looking at an anti-amyloid therapy, you might start it here. You always want to start these treatments when things are changing. That if it's flat, it doesn't give you very much information. So you want to see it just when it's starting to change. But here, too, we now know that this period between here and here is roughly 20 years. So if you're looking at new treatments, and the proposition of starting one 20 years early, you need more information on that. That's a very challenging type of drug trial, and you can imagine following someone for 20 or 30 years to try to measure something that's really having an effect. So we can go to tau, and that gives us a little bit of a compressed time window. But what we know is not a very good strategy is waiting till people are starting to show symptoms of Alzheimer's disease. At that point, we're seeing there is substantial cell death that really cannot be salvaged anymore. And we see that often the drug trial results for Alzheimer's disease and the treatment are unsuccessful, likely because starting a bit too late, not giving the drugs a good chance. So this I hope illustrates the need for the natural history type of study. We need to know this exact trajectory. We need to know the time difference between all of these things, and that can really help guide these and hopefully increase the chances of a successful trial. So with future directions, I think things look very promising. As I said, the government acknowledges this. Tremendous resources are being put into it. In 2017, they created something called the Alzheimer's Clinical Trial Consortium. And this was just infrastructure that the National Institute of Health set up so that there was trial-ready components for testing out new drugs. If pharma had a new drug they wanted to try, they could use this infrastructure that helped them design the trials and get going right away. What's exciting is we just got back from a meeting where looking to launch a specific consortium dedicated to Down syndrome. Okay, so that's just in the early stages. They acknowledge the value of using people with Down syndrome, that population, to investigate drugs. So I think without a doubt people with Down syndrome can benefit from the research going on. There's a new Include initiative that's just been launched by the National Institutes of Health, and this isn't just with Alzheimer's disease, this is just studying all conditions across the lifespan. And what we're doing, okay, my last figure is not showing up, but there's a study going on called the Diane trial, and that's where I was talking about earlier, people who can get early onset Alzheimer's disease. They have been gathered to form a clinical trial network too, because it's a group that really, knowing the age that their parent ended up getting diagnosed with it, will almost be the exact same as them. So you have a population, you know the trajectory, very powerful for trying to look at treatments and prevention type of things. And that trial has spun off what's called a treatment unit too, and we're hoping the same thing can happen here in Down syndrome. And I'll end it there. Lots of investigators involved in this, but we are not the most important ones. Of course, it's all of the participants and their family, just the most wonderful group of people giving their time that you can ever imagine. Almost everybody has a job. It causes them distress, but they'll take a day or two off from their work and come in and help us out and lay in the magnets and get poked with a needle to draw blood. But incredibly brave group, and we just can't thank them enough. So I can end it there. Thank you. I think I took the full course of time. I'm happy to take questions, but also if you want to break, you can do that too. So, yes.
Quick question. My father was late onset of the dementia, probably in the late 80s, early 90s. He died in 95. He wasn't, it hasn't progressed to we had to have him in assisted living for the last 2 years of his life. By and large, it wasn't nearly what it was if my mother-in-law came in. So I've been involved in testing personally through the Weizmann Center since 2003 when my father died.
Okay.
So my question is this: I'm getting all of this information. I'm part of a study. But at what point does an individual who is starting to have issues with this, whether they be an individual with Down syndrome or an individual like myself, at what point do they let us know that we may be at that point where we need to start doing something?
That's a great question. That's a great question. And I would say, as soon as we know, we're obligated then to relay on that information. And I think I am speaking perhaps too confidently or assertively that we know exactly, well, here comes the amyloid, you're going to get it. What we do find is there's a lot of people walking around with this amyloid in their brain that function just fine cognitively. In fact, if you looked at the older population in the 80s, you would see most people do and seem to handle it. So until we can really determine that it is predictive of something and really starting to tighten up all that information, and it's almost to that point. There's starting to be discussions of informing people of the status of that. But again, we have to know for sure before that information can be relayed to someone. So right now, we say that all of these studies, especially with the amyloid, are non-diagnostic. They can't provide a diagnosis. So I'm hoping we know more, and we will, as all of this data starts to come together. But of course, there's a very broad range, and I didn't even get into this issue of once somebody does decline of cognitive reserve, how certain individuals can seem to fare much better for much longer than other people in that same category.
And the other thing I want to ask about also is that my forgetfulness, my wife oftentimes tells me it's because of my Norwegian heritage, and I'm wondering if there's been any studies as it relates to that.
With Norwegian. They are active. I know Sweden is very active in all these. No, these studies are being done worldwide. So yes, I hate to say it, I might be younger than you. I probably am, and I get the same thing from my wife, and I hope that's not. I guess we call that selective hearing. Okay. Yes.
There's something called brain plasticity. Mersenek works in that. Do you that brain plasticity means where they develop a different pathway for these neurons? I'm just wondering your take on that. Is that effective? It almost seems like it's not.
Well, it's throughout the brain, right? So brain plasticity, is also strengthening ones that weren't previously utilized as much. Right. So in a case like Alzheimer's disease, you're seeing the brain is affected, throughout. So kind of strengthening other pathways is more of a challenge. But again, in this area that they call cognitive reserve, it could play a component in that too.
Could you explain that cognitive reserve a little bit?
Yeah. So it suggests that, for example, people with higher levels of education seem to get it later. And that might not mean they don't have the pathology. That just means they might be able to kind of go on autopilot a little bit longer before it's detected. So they kind of have the resources or efficiency in their brain in place that allows it to go and go on reserve. You know, run your gas tank on fumes for a little bit longer. Okay. Yes?
What is your take about people who speak different languages, like us? We are always into languages. Our brain is constantly into languages, going back and forth, with a lot amount of stress during any encounter. We go focusing very much, but then after I finish an encounter, it is like, a wave of, it's a lot of in my brain, at the end of the day I feel completely wiped. Sometimes I feel it's like, wow, is detrimental for me? Maybe I shouldn't do that many hours. Maybe that is contributing that I forget things, or not.
Okay.
One study says that if you speak two languages, your chances are less, or what do you think about it?
When you started, I thought you were going to go in the other direction, meaning your brain is working so hard, between languages that would increase that cognitive reserve, the use it or lose it thing. But it sounds like you were suggesting the other way. That struggle was causing stress, perhaps inducing forgetfulness at a younger age. I don't have any, off the top of my head, the results of multiple language or bilingual people and the incidence at the age at onset. I don't know. I'm sure it has been studied. Yeah, I think people are raising their hands and they want to answer. Go ahead.